Okay, we're going to get started with the next paper on flexible digital modulation testing for satellite regenerative payloads. My name is Darren McLernan. I'm a product marketing lead for the Agilent System View software, speaking on behalf of the author Greg Jew. And in this tutorial presentation, we're going to look a little bit at a evolution within the satellite industry from an old first generation set of satellites to newer capability and some of the testing and design issues associated with that generational change in satellite capability and some ways to overcome those issues. In the traditional or older architectures, the so-called bent pipe, a Earth station will upload a signal to a satellite which receives it and retransmits it down to the ground. So the problem being solved is avoiding the Earth's curvature, sending a signal to a wider distribution area and just bouncing it off a space station. So in the older satellite generation, there's a lot of the considerations were analog issues. You take the signal, you re-amplify it and broadcast it to the ground. So you're looking at flatness and linearity, and there's a number of issues over fixed bandwidths. What's happened with the newer generation of satellites is that with newer multi-antenna beamforming, you can provide signals unique to certain spot areas. You can provide different levels of services. You can reconfigure the bandwidth to have so much go to this service provider, so much go to another service provider. Space has become IP packetized, so there's networks in space. You take signals from the ground, demodulate them, get the bits, route them, and remodulate them and broadcast them and route them to different locations to provide an overlay level of services on the ground. So this complexity of reallocating spectrum, reformatting things, has put a lot of the intelligence up into the birds themselves. So with that, there's another set of design challenges and testing challenges that go along with this new capability. So in this new capability, where you may have been measuring frequency response or flatness and ripple, group delay, you're now measuring different quantities. You're measuring error vector magnitude. You're measuring bit error rate. You're accounting for more sophisticated block diagrams and actually treating the satellite itself as a receiver and a transmitter. So there's a whole range of additional capability that goes along with the new generations of satellites, which calls for new understanding of what measurements to make. So in older formats, they would generally use more simple modulation schemes. Here, BPSK is pretty bulletproof. It will go from between two states. Generally, because of the limited power, you're using a constant envelope type of modulation system. So 8 PSK going up to 16 and 32 APSK are the newer formats. What you find now is that higher modulation formats are being used to pack more bits per symbol, to deliver more data per unit time for a given amount of spectrum. So the spectrum occupancy is very, very high. Now in these formats, you have additional challenges with measurement quality. So before, when you're just hopping frequencies, frequency shift keying, or using simple modulation formats, you care a little bit less about some of these things. As you pack these modulation rings tighter, you begin to need to worry about how far each of these states is from each other. So noise and nonlinearities and different things affect the quality of the states. So some of the things that can go wrong that you'll want to measure are gain imbalance, a difference in the gain between I and Q, because you're working in an I and Q plane. You're working on skew, rotation, phase noise tends to speed up or slow down your carrier, which rotates you randomly along a circle and smears you along a circle. There's also, for amplifier people, you start having to worry about gain compression effects and a gain turning into an angle error or an amplitude error needs to be corrected as well. And all of these things, there's an ideal state of where you'd like to be and where your information is actually. And that difference is called an error vector magnitude, and that's an important measure of quality in a lot of these systems. One of the challenges of doing bit error rate or error vector magnitude is the ability to troubleshoot. With bit error rate, all of a sudden you get to the end and you either have a very favorable bit error rate, no errors, or you have a lot. And if you have errors, where do they come from? Where's the smoking gun? What's causing the errors? So it could be a nonlinear PA, it could be flatness, it could be spurs, it could be your A to D converter and clock skew and all kinds of wonderful things about A to D converters. It could be in your signal processing in the baseband. To debug this, one handy thing is to be able to use the exact same software measurement tools at every place. And the Agilent actually provides equipment for every place, logic analyzer, scope for analog baseband, modulated carrier analysis with instruments, and even before you even do any of this simulation, you can use the VSA software from a spectrum analyzer. You can actually use that inside a logic analyzer or a scope or in the simulation software. So by using the same measurement technique, the same filtering, the same kind of algorithms at every place in the chain, you can eliminate, you do apples to apples measurements and you eliminate some of the errors. It's easy, it makes the troubleshooting easier. So here's an example of using the VSA in a logic analyzer situation where we have a 21 pin ribbon cable looking at this Xilinx Vertex, looking at the pins, and it takes the individual pins off the bus and reconstructs what the sampled waveform value would be, because realize you probably have a serial stream of data, and it reconstructs the communication information from the raw data stream. So that's a formatting issue. When you get to modulated carriers, you're still using the same tool, but now you're working off a time-varying RF carrier envelope. Now, making signals is another challenge. For simple kinds of signals and investigations, people use inexpensive tools that they've made and download them to the instruments. There's also inexpensive test and measurement software to do this, Agilent Waveform Creator. Another scheme that you're seeing here is with a system simulator that SystemView, that Agilent, soon to be Keysight, sells. And you can see that you can choose from a whole range of modulation and also demodulation formats. There's a 40, and you can make more if you'd like. You can make any signal, add any kind of filtering and impairments, other signals, aggregate other signals, and download those. Anything in this simulation that hits one of these components is downloaded to a connected instrument. And with a wideband ARB, this particular ARB is capable of 5 gigahertz of analog bandwidth. You can then make a very wideband signal, typically hundreds of megahertz in the case of SATCOM, and upload it to whatever millimeter wave or X-band frequency that you'd like. Here's a picture of this. SystemView is actually running, the CAD software is running on a controller inside this card cage, and it's feeding the ARB through the backplane with data, and the ARB is making the signal, and it's uploaded to the PSG and then digitized with a 63 gigahertz oscilloscope. The advantage of an oscilloscope is you save a down conversion. You're directly digitizing the signal. So that has some advantages as well. So for a lot of satellite signals that are on the orders of hundreds of megahertz wide and then may have multi-channel applications, some of the traditional 160 meg wide measurement platforms may or may not be able to do that, and so you need at least a wideband digitizer with a down converter or a scope with fairly wide bandwidth to be able to capture those signals. Actually, it turns out that you can capture the signals and bring them back into the simulation software and continue to demodulate them. So that's kind of an interesting trick. Here's a case where I spoke earlier of, in the newer generation of satellites, you can reconfigure the bandwidth dynamically to reallocate for certain service levels to different people. Now, to do that, you're often looking at creating multiple concurrent signals side by side, and to do that, it's possible to set up multi-emitter situations and combine them with a resampler. There's a resampler component in this CAD software, the system view software, that will take all of the carriers, resample them to a common time step so that they're all one wideband signal, and then download that wideband signal and really make that signal. And this is a picture of it. So if you digitize this on one of the wideband digitizers, bring it into the analysis engine of the VSA software, you can actually zoom in and demodulate any of those individually, or look at the power, the ACPR, and different EVMs and quality metrics for any of the channels individually. It's important to exercise your power amps with realistic conditions that they'd really see. Another aspect is bit error rate. This is showing a personality for making both the modulation and demodulation. One thing that's shown here is packet error rate versus signal to noise ratio. Packet error rate is different than bit error rate in that if you have maybe a 6,000 symbol payload per frame, you'll have a lot of data bits in one frame. Does the frame have any errors instead of just one bit? So it's actually harder to do that over a whole frame, so your packet error rates are going to be higher. But again, you get into this debug thing of where was the problem. Another issue is coding and decoding. You don't just have naked analog components anymore. You have forward error correction and pre-distortion and a lot of signal processing applied to make the signal survive marginal analog conditions. So on this case, the packet error rate or bit error rate very often will go from being poor quality at very low marginal conditions, and all of a sudden the error correction will kick in and correct a lot of the errors. And so some of the modern techniques like low density parity check that add correction factors and make the signal very noise-like to approach the Shannon limits of how much information you can pack per hertz for a given signal to noise ratio is really pushing the envelope of what's physically achievable. So that just makes design and debug just a little bit more difficult because you have to consider these extra factors. So to summarize, the newer generation of satellites require an additional set of diagnostic and design techniques. You can combine simulation software and the instruments to create fairly complex scenarios of not only multi-emitters, but lots of impairments, interferers, and simulate more complete conditions to really wring out satellite qualification. Because once it's in orbit, what are you going to do? So there's a lot of testing that goes on ahead of time. The VSA software and the system view software can be used throughout the process in R&D, from concept all the way through debug and into qualification. And the ability to add known amounts of garbage, impairments, IQ offset, nonlinearity, interferes and noise and different fading conditions allows you in the R&D situation to really wring out a design much earlier in R&D before you finish the design. That concludes the remarks. If there's any questions, I'm happy to take questions, or we can go back to the Agilent exhibit, and happy to show you any of this. Okay, thanks very much.